Our today's session, we are going to compute the brightness or the apparent magnitude of all near-Earth objects in the pandas data frame. So what we are going to do is we compute the position vector of all NEOs, we compute the position vector of Earth for today's state, and then we are computing the corresponding apparent magnitude of all NEOs, and we will check if there are some outliers or not. And at the end of the session, we are going to compare the brightness values of the known objects with the NEO survey telescope called PanSTARRS to see, well, how many objects would be theoretically visible for this telescope that's whose specific task is to, well, discover new NEOs. So this is like a small quick overview, and of course the today's session is provided also on GitHub. The link is in the show notes or in the description, and you can go through the scripts, and if you like to know what is going on in each individual cell, yeah, just continue listening and watching this video, because after this short intro I will provide an explanation for each cell. At the end of today's video, I will also give a small outlook what we are going to do in our next session, because, well, the apparent magnitude and the known NEO distribution doesn't say anything for our task to determine or to compute a perfect observation strategy. So stay tuned until the end of the video as well. See you next time, and yeah, hopefully you will enjoy the video in the upcoming seconds. It's time to compute the NEO appearances in this session, in this script number 07 NEO appearances.ipynb. And to do this, well, we have to, of course, import some libraries. Well, the kernel needs to be started. We are assessing our NEO database here in cell number 2, and then in cell number 3 we are simply extracting all information from the database with the simple command select star from main. So extracting all information, and here in cell 4, let's take a quick look what we have. We have here different columns. Each column gives some information of the NEO, like for example the first one is the name, the epoch in modified Julian date, the semi-major axis in AU, eccentricity, and so on. And at the end we have the corresponding NEO class. And if you remember, we had the Amor, Apollo, Aten, and then also the inner Earth objects. And today, or yeah, in total, we know currently around almost 30,000 NEOs. So what do we need to do to compute the apparent magnitude? Maybe you recall from last time, we have to determine the position of a observer, in this case it's the Earth, and the position of the NEO with respect to an illumination source, which is of course the sun. And to compute these values we need SPICE this time again. So we need some SPICE kernels, like this SPK kernel that contains information about the planets. We need a leap second kernel, and we need a kernel that contains some parameters, some constants, like for example here you can see the G time M value of the sun, to compute the state vectors of the NEOs based on their orbital elements. So let's execute this cell. We are moving then forwards. Moving in cell number 6, we compute the ephemeris time for today's date using the SPICE function UTC to ET. So we use the date time now function, convert it into a string with year, month, and date, and then we convert it into an ephemeris time. And since we do not provide any time, SPICE is assuming midnight as the corresponding time. Now in cell number 7, we can then compute the vector from of the Earth as seen from the sun. So the position vector sun to Earth with SPICE CPI, SPK GPS. The target is the Earth, 399. The time, ecliptic J2000 is the reference frame. If you do not know a lot about reference frame, don't worry. I have also some scripts here in this GitHub repository and also video explaining the reference frame. And the observer 10 corresponds to the Earth, to the sun. And this is the position vector of Earth, of our home planet for today's date. Now, if you would like to compare this value, of course, always take NASA horizons, which can be used as a, let's say, ground truth. I compared all the values and they make sense. So these values have been compared already with some reference. For the apparent magnitude computation, we need to convert some parameters like some values from AU. We have to convert into kilometers, and from degrees to radians and so on. This is what we do here in cell number 8. And then afterwards, we can then compute the position vector of each NEO using the perihelion, the eccentricity, inclination, and so on, using the SPICE function conics. So what we do is here, but we also only need the XYZ values, so the position values, and we do not use the velocity values. So we do not need the state vector, we simply need the position vector. So this is cell number 9, executing this one here. And then you can also again compare this value now with the results from the NASA Horizons system. I already compared it. So the very first entry is 433 Eros. So take a look and you will see that the accuracy is quite nice and the value corresponds to what NASA Horizons provides. Well, in cell number 10, we need now to do some vector linear algebra magic. Well, actually, it's quite simple because, well, we need the vectors from the object as seen from the Earth. No, the other way around. The observer as seen from the object, so NEO to Earth position vector, and we need the NEO to Sun position vector. So this is like the object to illumination source. We simply invert it here, and here we do some linear algebra stuff. And then at the end, we need to convert it back from kilometers to AU, which is then done in the second part of cell 11. So let's execute this command here. And then we can finally compute our apparent magnitude in cell number 12. And for this, we use the function photometry.hgappmag. And this is a function we created last time here in our, I think it's the auxiliary folder. Yeah, there, photometry.py, where we have a Python function with the phase function and so on. So everything is documented here if you would like to have a deep dive into this. And also the last videos were talking about this function. So, cell number 12. Yeah, perfect. And now we can take a look to see whether these values make sense. So for example, yeah, we can take a look at the 433 Eros. We have an apparent magnitude of 13.3 magnitudes. If you compare it with Stellarium, Stellarium will provide a brighter value because I think they assume a different slope parameter. I think some default one, while we have the ones that are in the database. So yeah, you see here 12.8. Although it's, let's say, kind of bright for a telescope, it would be virtually impossible to observe because it's really close to the sun. I think Stellarium has also some kind of angle measure. And what we have is 11 degrees. So this is virtually impossible to observe. So we need like 20 or 30 degrees distance to the sun to have this thing, to have this thing observable. Now it would be really, unobservable. So this wouldn't quite fit. So now we can check the other apparent magnitude values. So for example, let's have a look at cell number 14. We check the apparent magnitude and we see that some values are exceeding common sense, let's say. Like for example, this object here is like -7, which is like extremely bright, brighter than, like a full moon brightness. Not a little bit fainter, but still. And it's I checked this object. It's a very small object, and in some databases it's listed as a very small object. In the NeoDice database, there is no value provided. It simply says, well, this is like a placeholder here, -9 absolute magnitude. The same course, the same thing applies also for the other object here. These values are for sure outliers. The same applies also for the last two ones with an absolute magnitude of 99. So this values here, this is like ridiculously large. It's completely, yeah, extremely dark and unobservable. So in line number 15, cell number 15, we are just dropping these 4 objects, and we will continue also in the future working only with the remaining 29,040, 45. At the end, what we can do is in cell 16, we plot the distribution as a histogram. Yeah, each bin represents one magnitude, so which is defined here in this part. And we want to make it a little bit comparable. And there is the website from Pan-STARRS. This is a NEO observation project. They say their exposure time varies between 30 and 60 seconds. And yeah, you can say roundabout the limiting magnitude is around 24. So let's draw a vertical line at 24, and let's see how the distribution of the brightness looks like and whether Pan-STARRS could observe anything at all. So let's have a look. And we see here, it looks, yeah, quite symmetric distribution, I would say, with a peak at around 27.5, so 27 to 28. And here is our vertical line of Pan-STARRS. So you see with the naked eye, well, it is like majority is invisible for the telescope. Only this fraction here is observable. So what we can do, we can simply count the values. And we see that of this, let's say 30,000, around 5,000 are currently observable, and the rest is not. This limiting magnitude computation, though, simplifies certain things. I don't know if I would like to present it next time. I think next time I would like to show this. I would like to plot these objects in a sky plot, so you see where they are. So it's not like every region in the night sky is interesting, so to speak, right? So there are certain areas of interest, but let's leave it like this today. And the limiting magnitude is also half the truth, because these objects, they have a certain, not appearance with the brightness in the sky, they also move. And if they move, they will also move on the pixels, because, well, if you want to observe new objects, you don't know which direction certain objects are flying. So you have to see after how many seconds, for example, an NEO is leaving a certain pixel, so it's not illuminating the pixel anymore and leaves to another pixel, creating like a line on the CCD. And this leads also to the problem that certain objects, although they may be bright, but if they are very fast, they could still be unobservable. So this limiting magnitude of 24 assumes steady state objects. So we will also consider in the future the apparent movements of NEOs in the night sky. So this is what we do in our future sessions. I think there will be 3-4 more sessions where we answer this, and then also using a model of NEOs. So we will not use the real data because they are in a way biased. We need an unbiased simulation data to work with it. And until then, I hope you enjoy some coding, and see you next time.